Hello, everyone. Thank you for joining. Today, we're going to talk about how to fight climate change by building sustainable software. First, let me introduce myself. My name is Ioannis Kolaxis. I am a software architect, and I work for Atos in Athens, Greece. I wrote a book on green software. I am an inventor, and I have filed 5 patents in the past 2 years. I have also won awards for 2 years in a row for coming up with the most innovative ideas at an innovation contest we run inside Atos, where all the employees worldwide participate. I have been building software applications throughout my career, previously working for IBM and Siemens. And this is my first in-person conference after a long time. The last one was in San Francisco, USA, where I spoke at Oracle Code 1. Climate change. We all know about the continuous temperature increase due to the different human activities in every part around the world. We all hear about the extreme weather conditions like floods and hurricanes. What can we do as software engineers to help prevent climate change? Is there anything we can do? Stay with me and you will find out how you can build sustainable software that doesn't impact the environment. First of all, I'd like to explain the problem so that we all have a common understanding. Human activities like burning fuels, burning coal and oil, produce gases known as greenhouse gases, such as carbon dioxide. These gases stay in the atmosphere and they trap heat, therefore increasing temperature. You can think of these gases as some kind of blanket wrapped around the Earth that increase the temperature. And the question is, who emits the most carbon? This is a quick quiz for you. Do you think it's the industry? If you think it's the industry, please raise your hands. Okay, thank you. Or is it B, transportation, like flying with airplanes and commuting with our cars? Or is it C, electricity and heat producers? And the correct answer is C. According to the International Energy Agency, the top contributor in carbon emissions is electricity and heat producers, accounting for 42% of the global carbon emissions worldwide. How does this relate to our work as software engineers? Our software applications run on servers. These servers are hosted in data centers and they consume electricity. Our users interact with our applications by exchanging data over the network, most commonly the internet. According to the International Energy Agency, data centers and data transmission networks consume approximately 2% of the global electricity, with data transmission networks consuming more than data centers. We all use nowadays applications like Google Maps to calculate our route from point A to point B. And Google Maps propose to us the fastest route or the one with the shortest distance. Nowadays, Google Maps provide an additional option of the most fuel-efficient route by taking into account some factors like the traffic jam and the slope of the road. How can we build our software applications so that our data networks consume less electricity? We can do it very much like in Google Maps. We want to move our data from point A to point B. And to reduce the electricity consumed by data networks, we need to minimize the distance from point A to point B. We don't want our data to travel around the world. That's why we must place our servers in a data center that is close to our customers, close to our end users. For example, if our customers are based in the Netherlands, we should also place our servers running our applications in the Netherlands. And we should always examine if it makes sense to transfer our data over the network. Many times it makes more sense to process data at their source, right where they are generated. So if it's a factory, maybe it makes more sense to place some servers in that factory that process all this data so that we don't have to transfer them over the network to the cloud. Besides minimizing the distance that our data travels over the network, we must also reduce the size of our data by compressing our data and also making sure that we filter out any unnecessary data. Many times we think, okay, it doesn't matter, this is all the data we have, let's transfer them to the cloud. But this is where sustainability comes into play. We need to consider if we really need the data we are sending over the network. If we don't need them, then let's filter them out and send only the data that matters. So remember, when you send your data, don't send them traveling around the world, but always process them locally if you can, and if you cannot, always choose the shortest distance and remember to filter out any unnecessary data. We've talked about how it is important to choose a data center in a location that is close to our customers. There is one yet critical aspect of choosing the data center. Depending on the region that our data center is located, some regions consume green electricity that comes from the wind and the sun, and therefore this is carbon-free electricity. Whereas there are some other regions that consume electricity coming from burning coal or burning gas or burning oil, which have high carbon emissions. Google Cloud provides data about their data centers, recommending the use of green data centers that consume clean energy. That's why you can always choose your data centers, preferring the ones that consume the greenest electricity and therefore have low or even zero carbon emissions. And even if one of these data centers is far away from your end users, you can still consider running some of your batch jobs, like the ones you usually run at night. You can run these at the data center that consumes green electricity, therefore minimizing the impact of your batch jobs, of your compute-intensive jobs. We've talked about how to consume greener electricity, but it's always more important to reduce the amount of electricity that our data centers consume. This is a diagram that looks very much like your own data center, where you see the servers running your applications. Up to 50% of the servers in your data center just waste electricity. These are redundant servers, and most of the time, they don't do anything useful. They just wait for a failure to happen to one of the active servers so that they can take over. And while they wait, they consume electricity and therefore emit carbon. Let's take a closer look at what happens. These are two identical servers, with the first one being the active one. Therefore, server A is the only one serving customer requests. It just waits, and we have the other server, which is in a standby mode, that just waits for a failure to happen. It consumes electricity without doing anything useful. It is an idle server. And when a failure happens to server A, we can quickly fail over to the other server that was until previously in a standby mode, so that we continue fulfilling user requests without the users noticing the failure. That's how it works. Speaking of redundant servers, this is a car with redundant engines. It has two engines, one engine in the front of the car and an identical engine in the rear of the car for redundancy. It was designed specifically for trips to the desert Sahara, where a failure in one of the engines could be fatal. It even has two petrol tanks, two different petrol tanks, again for redundancy. When you go for a safari trip to Sahara, then you should definitely choose a car like this one with two engines for redundancy. But when you go to the cloud, you don't need redundant servers. Can you think of an alternative high availability model that does not use redundant servers? With the advent of cloud and containers, Docker ones or alike, there are alternative high availability models where we don't need any redundant servers. Here we can see the differences between virtual machines and containers. One of the characteristics of containers is that they have a size in the range of several megabytes, which is orders of magnitude smaller than the size of virtual machines, which is in the range of several gigabytes. And the same applies to the startup time of containers. To start up a new container, it takes just a few seconds, whereas in order to start up virtual machines, it can take a few minutes. Here we see how we can adopt a new high availability model just by using containers. When there is a failure in one container, we can quickly spin up a new container instance without the end users noticing the failure, because it only takes a few seconds to start a new container instance. And that's how we can use the cloud and containers to adopt a new redundancy concept where we consume less electricity and therefore achieve a lower environmental impact for our applications. Remember, when you go for a safari trip to the Sahara Desert, then always choose a car with two engines for redundancy. But when you go to the cloud, you don't need redundant servers. Speaking of cars, modern cars have a stop-start mechanism for fuel efficiency. When you are with your car in a traffic jam, or when you are standing in front of a red traffic light, the engine stops so that it doesn't consume any fuel. And therefore, we increase efficiency and reduce the carbon emitted. Can you think of a similar example with software applications, where a software application keeps running, consuming electricity, consuming energy, although it's not processing any user requests? It's not doing anything useful. It's being idle. If you have applications that are idle for most of the time, waiting for a request to arrive, such as an HTTP request, so that they start processing something related to this request, then this is a sign that you can adopt a new model, the function as a service model for your applications, which works like a stop-start mechanism in your cars. So let's take a look at how function as a service paradigm works. In this paradigm, we take an application and break it into individual functions, many individual functions, with each one of the functions doing a single independent piece of work. Each function is executed only in response to a request. It executes in order to process this request, and if there are not any other requests pending, then it terminates. Therefore, this function will not anymore consume any electricity or CPU or memory. So if you have an application that waits for an event to arrive, such as an HTTP request, or a file uploaded to cloud storage, or waiting for a new message to arrive in a queue, or it could be some task scheduled to run at a fixed time, like cron jobs, then this is a sign that you can have your application re-architected to leverage this function as a service paradigm, therefore reducing the utilization of your hardware and making more efficient use of electricity. This is an example of serverless functions. So most functions as a service, as a paradigm, are supported by cloud providers like AWS Lambda, Azure Functions, and Google Cloud Functions, where the cloud providers don't require from us to provision or maintain any infrastructure. As developers, we can focus on writing our code, on implementing our business logic, and the cloud provider automatically takes care of scaling these individual functions. So when we have more requests, it will create more instances of these functions that will process the requests. And therefore, your code will be consuming energy only while processing requests. As an example, Microsoft Azure supports the languages shown in this slide for you to write serverless functions. And it's also common that serverless functions only run for a limited period of time. So the default execution time in Azure is 5 minutes. So you should only consider functions, serverless functions, for functions that have a small execution time. If your application is written in a different language, which is not supported by serverless functions, or has longer running times, then you could consider running your application, running one of the services shown here, like AWS Fargate, Azure Container Apps, and Google Cloud Run. And the only thing you have to do is to containerize your application so that it runs as a container. This provides more flexibility so that you can run programs written in any language. And it also allows you to support long-running tasks that run for days or even weeks. And the most important thing is that all the infrastructure is being taken care of the cloud providers. You don't need to worry about provisioning or maintaining any servers. So what we've learned here is that very much like cars that have a stop-start mechanism, you can implement a similar mechanism for your software applications by leveraging functions as a service, that is, running your code as serverless functions or serverless containers. We've been speaking a lot about cars, and one thing we all know about cars is that each car has a different impact to the environment depending on the fuel that the car consumes. We have cars consuming diesel, we have cars consuming petrol, and nowadays we have electric cars. It's clear to us that each car has a different environmental impact. Can you think of a fuel for software applications? What could be the fuel for software? It's programming languages. We have different types of programming languages, like compiled languages, such as C and C++. We have languages running on virtual machines, like Java and C#. And we also have interpreted languages, like JavaScript, Python, Perl, and Ruby. Can you guess which programming languages have a smaller environmental impact? Yes?
Compiled, I guess.
Yeah, you're right. According to academic research, compiled languages tend to be the fastest and most energy efficient ones, with C, Rust, and C++ being the most energy efficient ones. Whereas the least The least energy efficient ones are Ruby, Python, and Perl, with Perl consuming 80 times more energy than C. If your software application uses one of the most energy efficient languages, then you're fine. But what happens if your software application uses one of the least energy efficient languages like Ruby, Python, and Perl? What would you do? Should you rewrite your software application? It depends. You should ask some questions. First of all, is it an internet scale application being used by millions of users? If this is the case, then it makes more sense for you to rewrite your energy consuming components. So the next step would be to identify these energy consuming components in your application, identifying the most consuming ones, and then rewrite these components in an energy efficient language. Speaking of programming languages, Java is one of the most popular languages today for enterprise applications. According to a survey by JetBrains, it is the second primary language being used by professional developers. However, even today, Java 8 is used by the majority of these developers. 72% of them claim to use Java 8, although the latest release is Java 18 as of March 2022. What can we do specifically with Java applications to make them greener and make them more sustainable? First of all, modern applications of Java have several performance improvements that reduce the memory footprint of Java applications. Since Java 9, Java strings take up 50% less space, specifically for strings consisting of Latin characters. According to some tests, this enhancement helps improve the performance of Java applications up to 10%. Likewise, since Java 10, there is a new feature called class data sharing, where especially for applications, Java applications that run on the same host, such as microservices, we can benefit from this feature of class data sharing because all these microservices, Java microservices, are actually sharing the same cache, and therefore we have reduced memory footprint by 15%. So if you are running Java applications, remember to upgrade to the latest version of Java. Without having to rewrite anything, you can benefit from the advancements in the latest versions of Java, resulting in environmentally friendly applications. As a rule of thumb, optimizing for the cost of our applications running on cloud means that we are building more sustainable software. Let's think about that for a moment. Our cloud bills depend on the network traffic, on the network we consume. The more network traffic implies higher cloud bills. Likewise, the highest the CPU and RAM usage of our applications, the higher our cloud bills will be. So remember this as a generic rule, as a rule of thumb, that the less money you spend on cloud bills means that you have more energy efficient software. All the cloud providers have their well-architected frameworks, which provide some best practices for us in order to improve the cost efficiency and the performance of our applications. So for example, in Microsoft Azure, there is a score assigned to each application, and by improving your score in cost efficiency, then you are likely improving the energy efficiency of your application. And recently, AWS extended their AWS well-architected framework by including a new pillar for sustainability that provides more tangible advice on how to improve your applications to make them more sustainable while running in AWS cloud. As software engineers, we frequently talk about non-functional requirements like availability, scalability, maintainability, portability. There are many illities that we have to care about. Please remember to include sustainability in your discussions. This is the newest illity that we must consider when taking important decisions on how to design our applications. Many times, our customers may not need the highest levels of availability that we may think of. It helps having discussions to understand what the level of availability is and design our applications so that they do exactly what is expected. And the same applies in many other aspects for our software applications. Sustainability must be a core part of our decisions nowadays. I have written a book on this topic, providing some practical guidelines on how to design software applications, essentially aspiring to help software developers include sustainability in our discussions, hoping that each one of us with our contributions can help make software greener. And as each one of us contributes, all the contributions will pile up, essentially making an impact in preventing climate change. Let's summarize all the actions that we have discussed today in order to build more sustainable software. First of all, if you happen to have Java applications, please update them to the latest version of Java. You will be benefiting from all the latest improvements without having to invest in rewriting or re-architecting your applications. It's the lowest hanging fruit. As a next step, remember to reduce the data transferred over the network, always choosing the shortest distance to travel to transfer data from point A to point B. You don't have to send your data all around the world. As a next step, consider adopting an energy-efficient, high-availability model that leverages containers instead of redundant servers. You don't need redundant servers on the cloud. As you can see, the difficulty increases. That's why each step requires more effort in terms of development. So the next step would be to re-architect long-lived applications to short-lived functions, that is, serverless functions or serverless containers. And the last step is identifying components that consume a lot of energy and rewriting them using an energy-efficient language. And as an overarching theme, remember that reducing the cost of running your applications on the cloud is the best rule that you can use as a metric to keep track of whether you're going in the right direction or in the wrong direction. And it's also a metric that everyone in your organization can understand. Cost is something that everyone understands the same. So reducing costs likely implies that you're also reducing the environmental footprint of your applications. Now it's your turn. When you go back to work, what actions will you take to help prevent climate change? How will you improve your applications?